to design better dimensionality reduction? Well, we want to improve classification and dimensionality reduction in highly nonlinear data, and therefore improve classification accuracy after dimensionality reduction in data, in different types of data, and also tackle data dynamicity and nonlinearity, as most of the databases recently are dynamic and nonlinear, especially biological data and other types of data like structured complex image data and etc. Well, first, to design a good dimensionality reduction method, we explain about some of the common problems existing in the previous dimensionality reduction methods like PCA, like TSNE, like previous ICA methods in the literature. The first problem is curse of dimensionality. As the number of dimensions increases, the distance between each point increases in exponential way, and therefore we have to reduce this distance in a more deliberate and hard way. Nonlinearity. When we are dealing with nonlinear data, especially where the data are laid in a manifold, we have to use types of dimensionality reduction that captures these intrinsic nonlinearities between points. Therefore, kernel methods are used. But sometimes kernel methods are so complex and provide computational burdens for our task, and therefore we have to find other ways. Law of large numbers. As the number of the sample size increases, we have to have a more powerful simulator. A small sample size. As the number of sample size with respect to the number of dimensions is small, we have to regard more complex models in order to capture for shattering and for including all these dimensionalities, and we have to use more powerful dimensionality reduction methods for them. Other problem is rank deficiency. When we are dealing with data that has a correlation matrix of 2 dense with high cross correlation between different dimensions, then we are in a very big problem, and we have to first reduce dimensionality of data to the more intrinsic components, more principal components, and therefore dimensionality reduction methods will get so necessary. And the last problem in dimensionality reduction is central limit theorem, as most features are representation of some of other features, especially in the biological features where the sensors are so distributed and not focused on the region of interest. Therefore, in such problems where the data are so convoluted, the convolution methods in dimensionality reduction are so necessary to avoid central limit theorem. Well, all these problems are tackled in independent component analysis, because dependency criteria is a wide coverage method that covers a lot of areas like information theory, communication theory, complexity, and etc. But what is independent component analysis? Independent component analysis is a method to find independent components from the mixed data and find a distribution that is highly entropied and highly marginalized. Marginalization in the term of having dimensions that are statistically independent with respect to each other. There is a problem in communication theory called cocktail party problem, where the voice interference in a party makes it hard for a larger number of people in a party, for each of the persons, to understand their friend's voice. It is a linear projection of the mixed signal, where we have to find statistical independence, the projector. And in contrast to principal component analysis, this method not only tackles second order decorrelation, but also higher order of decorrelations, nonlinear decorrelations, higher moments, for example, second, third, and fourth moments of decorrelations with respect to each other, which is a generalized form of principal component analysis. But what are the applications of ICA? Well, I have 5 minutes to complete the theoretical aspect of ICA, and therefore I will go faster to the main methods. The first application is reflection removal, when the image of a tree is reflected on the image that we want to see, and therefore we have to reduce the image interference by background removal. Well, we evaluate our proposed method, our proposed dimensionality reduction methods, based on MNIST data, which is handwriting images needed to find and unmix different handwritings from each other. The second application is not unsupervised, in contrary to the previous application. It is supervised, and it is a classification method for non-voice removal, time series classification. For example, when we want to discriminate 2 types of imageries, for example, imagery of A vowel from imagery of B vowel in a brain-computer interface task, then we have to first remove redundant information, reduce dimensionality of the AEG data, and then send the reduced dimensions to a classifier in order to dissect between the states. we have an EEG data that we evaluate our proposed method on that. Well, there are other applications of ICA, like n-grams, attention mechanism, finding the distribution of data, and distributed word representations, like the one in natural language processing for language modeling. Well, we mainly want to improve independent component analysis methods in classification and denoising tasks. And therefore, that's why we use two related databases in the UCI for that. The key idea is to compare projection with its null space to extract independent components one on one and design a differentiable histogram. And the procedure for that is to design a loss function to overcome the previous problems of independent component analysis and pass it to gradient descent and then evaluate with some powerful metrics for not only analyzing independency between components but also analyzing the accuracy using cross-validation methods. There are some related works. Self-organization in perceptual networks have been proposed by Ralph Ringster, which discusses about how to design a projector, how to design a neural network by mimicking from the brain. He realized that we have to design the network such that the output of the network dimensions have to be as independent as possible from each other, so that we make the maximal entropy. We extract the maximal entropy of the information out of each dimensionality, and therefore it results to a sparsified number of dimensions, lower number of dimensions, as low as possible. Well, the related works for that have some issues. For example, they couldn't deal with unknown source prior distribution. They could not find accurate result for complex images. They are highly computationally expensive. And these methods are hardly extendable to higher dimensions due to their complexity, especially because these methods really want to find the real distribution of those data and parameterize that. But when it comes to finding that, they have to use mixture of models, for example, Gaussian mixture model, and etc. But such models are so complex and are iterative without any closed form, and therefore they usually get caught into local minima and etc. To reduce such problems, we first look at the concept of analyzing independent dimensions more directly, not from the viewpoint of nonlinearity. Therefore, we use the Bayesian law, which simply finds for the dissected distributions, for example, the projection and the other dimensions, one dimension and the other dimension, such that this one dimension is marginalized and can be written in terms of product of two distributions. It is a definition of marginalization. By using such simple method, by using such simple idea, we want to outperform the previous state-of-the-art method of independent component analysis. Therefore, our designed objective function has to iteratively find each projection and their corresponding null space in each try, so that the Bayesian rule is satisfied, which is the ultimate satisfaction of the Bayesian rule is that marginalized product equals to joint distribution. To find the null space in such a way that it is gradientable and it is learnable using gradient descent methods and backward differentiation methods in the libraries like PyTorch and TensorFlow, we used householder null space rule, which is out of the scope of this description and is so statistical and linear algebraic, and therefore we don't go into it. But we can say that it is the formula is this, which is a function of the main projection. V is the main projection, and therefore, as we want to find V, which is W product by data, therefore it can be gradiented and can be differentiated in the backward methods in the libraries, making the optimization process through stochastic approximation methods. It is a sample run of code on synthetic mixed uniform data, where the iteration, as we see during the gradient descent, tries to marginalize the data so that the product of each distribution, each point in the joint distribution space equals to each of the marginalized distribution of which is projected focus on each of the lines, each of the axes. Therefore, the procedure for writing the code is that we first compute this loss function using forward projection by defining two types of function. First, one-dimensional histogram, and second, two-dimensional histogram. And then we compute the gradient change by PyTorch backward function. We use all PyTorch functions, therefore the PyTorch can automatically get the gradient in its pipeline. To make histograms differentiable, we use fuzzy membership functions, which are either sinusoid functions or Gaussian functions, which in each bin of histogram, the closer the point to the center of the histogram, the higher the fuzzy membership value. Well, we go to the databases that we have used in order to test our proposed method. First, we use MNIST data. As we see in the image, there are plenty of numbers written by previous writers. We have to combine these numbers in order to make a mixing matrix, mixing data, and then we pass this data to our method in order to extract and reconstruct the unmixed data, which is the original data here. Therefore, we extract this from this. To evaluate our method, we use MRE index, which is a measure of identityness of mixing matrix with unmixing matrix, produced by unmixing matrix. First, we explain the results over our MNIST database. We realize that our method has outperformed the state-of-the-art independent component analysis, which has been proposed in 2018. And we realize that our method is more accurate in most of the reconstructions, in most of the numbers, in contrast to the state-of-the-art method. We see on the images that it is the numbers reconstructed are so vague, but in our case, for example, number 2, number 8, number 5, number 4 are clear. And in terms of mean square error of the reconstruction with the main data, the original data resided here, we realize that our mean square error are the least in most of the images. The second data is EEG data. In contrast to the previous data, which our objective was to test unsupervised method for noise reduction and interference reduction, in our second database, we are planning to test data classification accuracy over our method compared with the previous state-of-the-art methods. Therefore, we measure a nonlinear dynamic biological data in a brain-computer interface task in our lab. The data are speech imagery, which is recorded while the user, the subject, imagines different vowels, different sounds in his head, in his or her head. The reason for choosing this data is that EEG data is, like other biological data, are so nonlinear and state-based. Therefore, we want to test nonlinearity and whether dimensionality reduction on nonlinear data works good or not. The database statistics are mean variance set, which is selected for 4 component case of source data. The selection is based on the tuning method that tunes these parameters and gets the best result. The data is a speech imagery dataset designed by Rostami et al. In our previous lab, and there are 6 subjects, all right-handed. 16 electrodes are put over the head of each of them, and the sampling frequency 512 Hz is recorded signal frequency from each of them. They first fixate on a point, and then a phoneme shape comes up by the stance of the lip, and then they imagine the stance of the lip and the sound of the speech in their head. For example, U or E vowels. The evaluation method is based on cross-validation method, which is 5-fold cross-validation methods. And the classification accuracy over discriminating between 2 classes is derived. Well, the results show that our proposed methods have outperformed the accuracy in 5-fold cross-validation compared to the previous methods, especially the state-of-the-art method. We have conducted the results on 2 cases, one without regularization, which we didn't use any L2 norm regularization, and the second one with regularization term. In both cases, our proposed method have outperformed. And the third parameter settings is the Amari metric that we have introduced before. This metric measures the independency between the finalized mixture and the finalized dimensions after imposing the proposed dimensionality reduction method. Therefore, we realize that our approach finds more independent components compared to the previous approach, which is aligned with our assumptions. The parameter tuning method we used in this study can be downloadable in our GIT hub, which is a generator that combines different types of classifiers together in a Python and then extract all of the parameters and hyperparameters needed in the case of tuning. Well, after imposing this tuner method, Our finalized hyperparameters are shown in this table. We designed our termination criteria to this number. As lower than these numbers, we're providing overfit. We use maximum iterations to 40 as higher iterations, but brought about overrepresentation to the data, and we tested it out. The number of default order of non-Gaussianity is set to 4, as higher order of non-Gaussianity for both NNIST and EG data were too high. And the noises would make the result worse at those cases. The fuzzy histogram parameters are set to fuzziness degree of 2, which is the Gaussian function, not sub-Gaussian or super-Gaussian functions, which the fuzziness degree for them are lower than 2 and higher than 2 respectively. The number of histogram bins are set to 15, as the higher histogram bins were so problematic in this case and provided so many computational burdens at that. And the membership parameters set to 2 and 2 for mean and variance. Well, we conclude that our method improved accuracy compared to previous state-of-the-art dimensionality reduction methods. We can implement this theory on NLP data and also on speech data, which we have written the sample codes for dataset generation, but we didn't have time to implement our method, and we will implement on that at a later time. Thank you so much for your patience and attention. We look forward to having your questions.